Hello everyone, this is Robert Hodges and I'm happy to welcome you to my talk on 5 great ways to lose data on Kubernetes and how to avoid them. It's an honor to be presenting at KubeCon Europe 2020 where this is a great conference, a lot of really wonderful talks, so we're just totally happy that to be selected. The topics that I'll be talking about are things that my company and my colleagues have dealt with from day to day over the last couple years, so we hope that you will enjoy the information we're about to share with you. Speaking of my company, let's do some introductions. So my name again is Robert Hodges. I am the Altinity CEO, but more relevantly for this talk, I have a long background in data. I started with my first database management system in 1983. I've been working on them databases of one kind or another almost continuously since then, with some short jogs into things like virtualization and security. I've been using Kubernetes since 2018. My company Altinity is an enterprise provider for ClickHouse. So we provide services and software for the ClickHouse data warehouse. It's a very popular, very fast open source SQL data warehouse. Again, most relevantly for this talk, we are the implementers of the ClickHouse Kubernetes operator and have made a major commitment to operating data warehouses in a cloud-native fashion on Kubernetes. And that work is the source of a lot of the information we're going to provide in this talk today. Before I get started, I'd like to just define a couple of things so that we have the right frame of reference for thinking about the problems of data loss. So the first thing is just to define, what do we mean by data? In a nutshell, data is any information, for the purposes of this talk, is any information that is used to either operate or guide a business. In the example I'm showing you right now, we see a typical table from a data warehouse containing sales data. So data warehouses are used to answer questions that often go to company strategy and tactics, such as which products have the best gross margins over time. If you can figure that out, you know which products make the most money and the ones that you want to focus on selling. Similarly, if you can answer the question, which kinds of companies are most likely to buy SKU 556, that's a product, then you can direct your salespeople to the places where they're most likely to make sales and bring home the bacon. Similarly, we want to define what we mean by the word lose. Well, in the context of data, lose is actually a spectrum. It's not a single thing. So when we lose data, we can talk about losing it temporarily. So it can be just gone for a while, but come back completely, all the way to a state where it is completely gone forever. You will never see it again. You will feel awful, and it's just vaporized. So I call this the data loss arrow of evil. And what's kind of interesting in when dealing with data is the value, depending on what kind of data you have, the loss may be more or less severe at different points in the spectrum. So for example, if you're running MySQL and using it to operate an e-commerce site, if MySQL is even unavailable and the data is not accessible, it means you can't sell anything. So you're basically at a standstill. For data warehouses, that's not such a big deal. They often offer, many of them, particularly if they're batch-oriented or doing answering strategic questions, may run sort of on a 9 to 5 basis. So having it down for a while is not such a big deal. On the other hand, losing some big chunk of data means that you lose vision on what's the state of the business. So that can be a very serious problem. In both cases, and for other databases as well, there is a point where it's all gone, and the result may be in many cases that the business simply stops functioning. So this is a very serious problem. So with these two definitions in mind, we can now step in and look at some of the different ways that we can lose data on Kubernetes and how we avoid them. So the first problem that I want to discuss is what I call the single copy catastrophe. This is pretty obvious from the name. But first, let's start by praising Kubernetes. One of the things that is wonderful about Kubernetes is how easy it is to set up complex applications. In this particular example, I'm going to use Helm. So Helm is a popular tool to create deployments in Kubernetes. Bring them up, you can upgrade them, you can take them away. In this particular example, I'm going to create a namespace, MySQL, using kubectl. I'm then going to run a single line helm install command to install a MySQL server, which will then pop up and run. And a few minutes after, or even a few seconds after I run this command, I will see a database running in a pod on Kubernetes with an attached persistent volume. Unfortunately, this database is kind of a delicate flower, and particularly when we're thinking about data loss. So there's a number of bad things that could possibly happen. You could delete the pod. That's usually not a big deal when you install from Helm. But it's possible that if you delete the node, you might lose the storage, because in fact the storage could, you don't know for sure unless you check, but the storage could be allocated locally. And for sure, if you delete the persistent volume, for example, if you allocate block storage, your data's gone. There's no replacement. And this is kind of the same situation that you have if you have a laptop and you drop it, lose it, or something the storage dies. So it's gone. So databases have dealt with this problem for a really long time, and the solution in just about every single case is to have replicas. So you have different kinds of copies of data, which mean that if you lose your main copy, there's another copy you can use instead. And MySQL is kind of instructive because it illustrates very well the two main styles of replicas that we get with databases. So MySQL, as you know, if you've have experience directly with MySQL yourself, has very good built-in replication. And so replication enables you to have live copies. You have a primary MySQL server. That would, for your e-commerce site, that would be where your transactions run. It has storage attached to it. And then you have MySQL replication enabled, and it goes, as soon as a transaction commits in the primary, it immediately transfers it to the replica. It's very fast, often a second or less to move transactions across. So what that means with this live copy is that if you lose the primary, you can just promote one of the replicas and you're right back in business again. The other kind of replica is a static copy, which is represented by a backup. So you can take those replicas, and this is again a very common way that this is handled in MySQL. From time to time, you'll run a backup of the MySQL replica, and then you'll store that backup in another location in case you need to make more replicas at a later time. So static copies and live replicas, these solve the problem of what to do when you lose your data in your primary database. So the issue, though, when you come to Kubernetes is how do you actually implement this in Kubernetes? Because we're talking, at the very least, a complex deployment with a couple of different types of servers running in separate pods. We have backups. And in fact, as we get to other types of databases, these may be far more complex. Modern databases are typically very complex distributed applications. So the question is, how do we set this up in Kubernetes, especially in cases where we might have to create dozens of resources to implement the database in Kubernetes? The answer that's evolved over the last few years is something called Kubernetes operators. So the way that what a Kubernetes operator does is it allows you to create what are called custom resource definitions. So instead of thinking of the database as a collection of deployments, stateful sets, services, pods, you instead have a new resource which represents the entire structure of the database. And so what happens is you load this custom resource definition into Kubernetes. It is Kubernetes API recognizes that it's handled by a particular operator type. It dispatches it to the operator, which then looks at it and decides what changes it needs to make in Kubernetes to implement the database. So what it then does is from there, it will set up things like stateful sets or services or pods or persistent storage, define them in etcd, and then the native controllers will take over actually implementing the database out in the Kubernetes cluster itself. And the result is a best practice deployment which contains all the pieces, including things like replication, possibly backups, that you need to ensure that you have adequate replicas to protect your data. So, and just to illustrate, what we show on the right here is a data warehouse setup. These are relatively complicated, especially compared to MySQL. Let's just have a look at the CRD. You can see from this that, in fact, what this does is it is much simpler than, for example, having to do the deployments directly and do all the low-level resources. We have a single, very simple resource file. This is actually a real resource file that you could load, and it says, let's have a cluster named CH01, actually with a configuration called replicated, 2 shards, 2 replicas, and then point to Zookeeper, which is used to keep track of state between the replicas. That's it. So this illustrates how much the operators simplify this and then also handle the issues of ensuring proper replicas, as well as many other things that are necessary for databases to function. So this is a huge step forward and is really one of the ways that we can implement replication and backups in databases on Kubernetes in a relatively straightforward manner. So that was the first. So replicas are one of the first solutions to losing data. Let's look at some of the other ways that we can lose data. So the next one is what I call blast radius blues. And let's talk about this term. It's one of my favorite terms from the high availability world. The notion is a blast radius is how far away do you have to be before you're not affected by a failure. And there are various, you can think of this as a bunch of concentric circles. For example, if a host fails or something on the host ceases to work, anything running on that host and potentially any data attached to the host may become available, may just disappear. So that's a relatively constrained failure, but they can of course extend out to cover much more ground. So for example, hosts are in racks are in data centers. It is possible to have failures which make data completely inaccessible across a data center. So for example, the failure of network attached storage, or a failure of the network itself, which can either cause data loss or unavailability. Beyond that, you can think of a failure at the level of a Kubernetes cluster, so that things within that cluster become unavailable or unusable. And then, of course, a failure within an entire region. So, for example, you can have failures there have been historically failures in things like Amazon that caused entire regions to lose access to critical services and even data across a number of data centers. So the really key thing to avoid blast radius problems is to get distance between your replicas. And for that, there's an incredibly helpful concept in Kubernetes called affinity, which basically gives us the ability to move pods around as well as associated resources like storage into different locations so that they are far enough away that if one thing fails, it doesn't take all your data down with it. So here's a simple example, a very simple example that illustrates affinity as well as its opposite, which is anti-affinity. So in this particular picture, we have a couple of Zookeeper pods. Zookeeper is a very popular distributed directory service that maintains consensus across a number of nodes. It's used for things like leader election, as well as holding distributed logs, anything where a series of processes need to agree on what the state of things is. It's really important with Zookeeper to have the nodes separated so that a failure will not take all of them down. In this particular case, what we can do is we can use anti-affinity to keep 2 Zookeepers from showing up on the same node, in this case host 116 on the left. Similarly, we can use affinity to drive that Zookeeper 1 instance to a host that has particular characteristics that interest us. One common use of affinity is to drive the pods, it's basically to separate the pods across availability zones. What I'd like to do is show you the code that implements this because it's a very powerful feature inside Kubernetes. So let's first look at anti-affinity. So this is pod anti-affinity, which basically is going to drive the pods apart and keep them from landing being scheduled on the same hosts. So what you see here is a part of a pod definition, and under the spec we have affinity rules, and we have a rule for pod anti-affinity. And we say that this is a rule that is going to be used during scheduling, so when we're starting the pod, but then we don't care later on while the pod is actually running. And what this syntax says is that there's a key host name, and we don't want to have two people, basically two pods, in this case from from one of our data warehouses. We don't want to have two pods from the same data warehouse on the same host. As you can see from looking at this syntax and even hearing me read it, it's a little bit non-intuitive, and we'll get to that because that actually turns out to be an issue. But if you get this right, what this will do is drive the pods off you will never get two pods scheduled on the same host. Now what we can also do is move pods to make them schedule in particular locations, and for this node affinity is very helpful. What we see here is node affinity, which is going to assign a pod to a particular availability zone, here US West 2. So and in this case, what we see is the key is the failure domain, blah, blah, blah zone. That is a property that's automatically set in most Kubernetes clusters. And we see that the value that we're looking for is US West 2A. So what this is going to do is any pod that contains this is going to want to land in US West 2A when it gets scheduled. One of the things that's kind of interesting I should note here about affinity is, particularly availability zones, is we have found in our work that it's best, if you're really concerned about distribution across AZs, it's best to be very explicit about it, as we show here. There are sort of tricks you can use that, for example, will get node affinity perhaps across a stateful set, but we find them difficult to configure, and it's just better to be totally explicit about where you want things to land, which means that different pods within a database cluster will actually have different affinity rules. The result, when you get it right, is that you get distance between your replicas. So in this illustration right here, we're showing a couple of shards on the data warehouse. That's ClickHouse. And then we have 3 Zookeeper pods. So that's a Zookeeper ensemble. We have the replicas neatly spread across the availability zones, US West 2A, B, and C. And so that spreads the data. The other thing that I want to draw your attention to is the backups. So if you take backups, a really smart thing to do is stick them in object storage. This is common just because object storage is convenient and relatively inexpensive. But the other thing about object storage is that it's self-replicated and can be quite distant from the systems that you're backing up. So for example, you can set up replication automatically across regions. And what will happen is that means you have a backup that's even outside the region that you're currently working in. So the topology that we're showing right here with the distance between replicas is actually quite common in Kubernetes, and is very easy to implement with things like kops, with AusEKS, and other types of managed Kubernetes. So definitely something that you should use to protect data. When we're talking about blast protection across regions or Kubernetes, in other words, sort of wider out in these concentric circles, dealing with things like the loss of a Kubernetes cluster, the loss of a region, this is no longer a data problem, but more of a question of losing IT resources entirely. So it's much more of an exercise for the reader that doesn't just include data, but includes things like, hey, how do we handle networking? How do we handle DNS? Things like that. So that's really beyond the scope of this talk, although it's something that people commonly do. So what we'll do is we'll leave that here and let you work on that yourself. Meanwhile, what I'm going to do is proceed to another kind of data loss, which is directly related to Kubernetes itself. And that's what I call affinity afflictions. So affinity rules are great. But one thing you should do is you should definitely check that they're really doing what you think they're doing. Here's an example. So we have a Zookeeper ensemble, which I set up as an experiment. And what I've run is a kubectl command to show where the pods are running. And the first thing that I notice is, even though this Zookeeper was supposedly properly set up and is something that I expect to run in production, I notice that 2 of the pods are running on the same host. So that's a little bit spooky. The other thing that I notice is if I want to go check where those hosts are and in which AZs, I can see that they're spread out across 2 AZs. So that's good. what we can do is take these two things together and draw a picture of how the zookeepers are actually distributed. And what we see is we've got 2 on one host, 1 on another, and the fact is that the distribution here is essentially random. It's sort of luck of the draw that we got 2 on one machine and 1 on another. The fact that they were if they had come up as they could have come up all on different machines, or we could have even have had all pods on a single machine. And what was actually happening here in this particular case is there just weren't any affinity rules. And this is so one of the things that you do want to check for is that if you think you have affinity rules, you want to make sure they really are there. And in this particular example, what I did was run a variation of the kubectl get pods command, and this shortened version with JQ allows me to pull out the affinity rules so that I can look at them quickly. And what I can see here is that they're null. There's simply no rules at all. So obviously affinity doesn't work if you don't use it. But the other thing that you need to do when you're checking these rules is to make sure they're really doing what you expect. As I mentioned before, the syntax for affinity rules is non-intuitive. I think that's a kind of a kind word. So it's pretty easy to set things up that look correct, but then actually behave surprisingly when they're deployed. So again, double checking the affinity rules, and as well as the actual implementation where the pods actually land is super important for using them correctly and protecting your data. Let's move off affinity rules to another one of my favorites, and this is a problem that I call the persistent volume that wasn't. And this is surprisingly common. I've probably hit this at least a dozen times in different forms. Let me talk about a couple of common ways that this can occur. Before we go anywhere, it's important to recognize that in Kubernetes, ephemeral storage is not a bad thing. It is a feature, not a bug. That's in fact one of the things that makes Kubernetes so powerful is you can have different kinds of storage, and we're going to take advantage of that in just a couple of minutes. But this is a picture of 2 Kubernetes nodes, and one I call the bad pod. It has a bad pod running on it, and it has no block storage. It's just writing to the ephemeral file system in the pod itself, like overlay FS. The other one is a good pod, and that's actually got nicely allocated block storage. Now what's interesting is as far as the applications are concerned, they can't tell the difference what kind of storage you have. The pods work in both cases. They answer API calls, so on and so forth. Everything looks good. What's even more interesting is the pods themselves cannot necessarily tell whether they have truly persistent storage because they just see it as mounted in the file system. So in Kubernetes, to say something is bad and to say something is good, well, this is in the eye of the beholder. If it's a web server, of course, it's fine. We don't really care whether the storage is ephemeral or not. If it's a database, of course, that could be quite a serious problem. So one of the things that you want to do is, particularly when you're dependent on assuming that persistent volumes have been allocated, is to make sure they're really there. So here's an example. We run a kubectl get pvz command, and I've changed the output a little bit so that I can make sure that we really see what we expect. And when we look at the PVC, we see that it has a storage class of COPS SSD 117. That's the storage class for COPS running Kubernetes 1.17. That looks pretty good. Moreover, under volume, we see there's a real PV out there. So a persistent volume has been allocated. We could actually check that using a get PV command and look at that. Another thing that's important is to look at the storage class itself and make sure that it's using a provisioner we expect. So the provisioner is the thing that actually goes out and allocates the storage. And again, our class here is COPS SSD 117. Its provisioner is the Oz EBS storage provisioner, which goes out and allocates block storage. So far so good. This actually sounds really good. This is allocating block storage. It should stick around when pods get restarted. Everything looks copacetic. However, that's not to say that we're fully protected. So, because persistent volumes are only good if you actually use them. Here's an example of a bug we hit with Zookeeper. It fortunately did not lead to a down system because we detected it in time and were able to correct it. But what happened was due to a misconfiguration problem in our Zookeepers. We had the EBS storage mounted as varlib zk data, but we accidentally set the configuration file so that Zookeeper wrote its snapshots to data and its log to data log in ephemeral storage. And the problem is that you, of course, can't tell that this is happening until you actually restart the Zookeeper node. Now, with Zookeeper, there's another interesting variation that it's not even enough to restart Zookeeper to see this, because Zookeeper replicates automatically. So in this particular case, we had an ensemble of 3 Zookeepers. When individual pods restarted, they would then connect back to the other 2 pods, get the data back, and so it would be transparent that we had lost data. The Zookeeper replication behavior was hiding this. It was only at a certain point that we accidentally noticed that the storage was not there and realized we had a real problem. So you really want to be very careful about this, and this is an example of an area where the answer that to solving this kind of problem is testing, and a lot of testing. So for example, just be super paranoid. Check that Kubernetes resource definitions are out there, as I showed before. Look at file system mounts. Make sure that the mounted file system matches where you that the PVs are mounted exactly where you expect them to, and you're writing to them. Kill pods. That's the best way of, if they're just single databases, if they lose their data, then you'll detect that. You can kill nodes. You can kill and restart all pods in a replicated database. Deleting volumes is a good thing. So take the volume away if the database is truly dependent on it and it's pointing to it and writing to it. The database should stop working. And finally, test with huge amounts of data. Many database problems are revealed only when you have a large amount of data. In this particular case, if you add a lot of data, it will fill the local file system, and then you'll quickly see that you've got a problem because you're not even writing to the block storage. So with that, we've shown 4 ways you can lose data. Here's the last one, which I call fat fingers of fate. And this is probably the saddest one, because really, if you think about it, the best way to lose data is to do it yourself. And the virtue of Kubernetes, of course, that we can create things, has this mirror image that we can, or sort of equal and opposite effect, that we can take them away just as quickly as we can create them. So this single line command will wipe out that MySQL database that I created as an example at the beginning. So that's it. Data's gone. So one of the things that, given how easy it is to destroy things accidentally, one of the things that's worth thinking about is how to protect your persistent volumes so that they don't just evaporate. And it turns out that we can do this through what are called reclaim policies. So we list the PVs here, and I show this example. You can see the policy is delete. That means that when the persistent volume claim that caused the storage to be created goes away, the storage just vaporizes. So that's bad. What we can do if we have existing PVs is we can fix this by changing the reclaim policy to be retained, and this patch command shows how to do that. Another possibility, if we want to do this in a general way, is to create a new storage class. So the Kubernetes is really flexible, and this is a great example of where that flexibility really works for you. I've created in this definition a storage class, which is exactly the same as the normal COPS storage class, except that it by default uses retain as the reclaim policy. So any persistent volumes allocated with this will have retain as their policy. At that point, if I destroy MySQL by accident, I can reclaim the storage just by making a persistent volume claim that matches the volume that we're trying to attach to in every respect. And this is something where you have to be quite careful about it. So for example, you must have the volume name stuck in your persistent volume, otherwise it won't match and it'll just stay in a pending state. But if you do this right, you can recover storage quite nicely. And in fact, here's the process that you go through to reclaim: is you've blown it away by accident. Just go in, remove the claim ref from the PV that says, hey, it's now free to be reallocated. Go ahead and run that definition again to create a new persistent volume, and then, or persistent volume claim. And then with Helm, it actually has a feature which allows it to reattach to existing storage, and you get your database back. And that solves the problem. So with this, we've covered 5 ways to lose data, talked about solutions. I'd just like to summarize by thinking not so much about the ways to lose data, but about the things you want to do to solve those problems. So the core of solving problems with data loss in Kubernetes is just to be exceedingly paranoid. This is something that's true of data in general. And then beyond that, there are 5 specific things that you want to do. First of all, have replicas of data. Always, extra copies are always good. Separate them by distance. Use affinity rules so that you can lean on the Kubernetes capabilities that allow you to spread pods across, sort of across availability zones. This is a great feature, and keep them from clustering on single nodes. Use reclaim policies to protect your storage, and then finally just test the daylights out of everything. If you're in data, this is something you just becomes part of you, that anytime you have data, just do all kinds of tests on it, because this is the best way to find problems before they actually occur. And then finally, if you have operators available, check them out and use them. They're a wonderful feature of Kubernetes and very, very useful. So that's it. I hope you've enjoyed the talk. It's been really fun putting this together and presenting it. I just want to say as a final note, we are hiring, like any self-respecting startup. If you like this talk or think you can do it better, please give us a call. We'd love to talk to you. Our own operator is shown here in the GitHub reference. So check it out. There's many other great operators. Percona has a great one. There's good operators for Zookeeper. It's an increasingly powerful paradigm, and definitely something worth learning about. Thanks, and I look forward to answering questions.